Hi everyone. In this video, I want to take a look at fatigue and kind of do a general overview of fatigue and some of the considerations that we have to take into account. So what I have here is a small component that came off of my snowblower this weekend after a particularly large snowstorm, about halfway through clearing my driveway. And if I could show you a close-up view of the end of this and kind of look at the geometry closely, what I might find is that we have a pattern that emerges. And the question then is, what can this pattern tell us about how this part failed? Now, realizing that this is a component from the snowblower that sees what we would call a cyclic loading, meaning the load varies over time in a repeated pattern. So looking at this cross-sectional view of my component, the one thing I can probably say is that I believe the failure started right about here. And the reason I know this is that these lines represent a propagation or a crack propagation originating at that failure point and spreading across the part. So then why does it look different over here? Well, the likely answer is that this crack slowly propagated over time, and then eventually the part failed statically and rather dramatically because the cross-sectional area could no longer support the load that was being applied, and therefore it had a high stress, it exceeded the failure stress of the material. Now, what I would see is if I looked closely at this component, this area with the ridges is relatively smooth. And we find that because over time, as this crack is propagating across, these two surfaces are now rubbing together with every little movement that's happening within the snowblower, and they're rubbing together and smoothing out any imperfections that we would see there. So this type of failure pattern likely tells me that this was a fatigue failure. So when we consider machine components and different kinds of machines, I'm likely to find that fatigue failure is a common mode of failure. So consider a part of an automobile. This is a McPherson strut, and within this assembly there are a variety of components. But what we are really thinking about at this time is what sort of loading is applied to these components. So as this wheel travels over the ground, it is going to be subject to bumps and potholes and speed bumps and things like that that cause the wheel to go up and down, applying a varying load up and down with time. So let's suppose that we could approximate that as just some sort of standard varying load. So as this loading is applied and removed and applied and removed, the components within this assembly see stresses, right? So recall what we've seen before, that if I take a cross section within some random part, I can have a variety of loads associated with that. So I might have an axial load, I might have a shear load, I might have a moment, a bending moment, and I may have a torque. Now, each of these arrows represents a possible load. Not necessarily comprehensive, but comprehensive from the perspective of various things that we need to consider. So we take those and say, okay, we have axial, transverse shear, bending moment, and torsion. From those, we can compute some corresponding stresses. So we have axial normal stress, transverse shear stress, bending normal stress, and torsional shear stress. And we also have some relationships for those on the basis of the loading applied and some various pieces of geometry. And we've seen all of this before. So previously, when discussing this from a static standpoint, what we need to consider are failure theories. And the failure theories, such as the max distortion energy theory for ductile materials or the Moore's theory for brittle materials, tell us that at some level of loading and therefore some corresponding amount of stress, we would expect this part to fail due to a static loading. However, when we talk about fatigue, we're talking about a variable cyclic loading. So the stress is not static, it's rather dynamic. And we expect that that cyclic loading will reduce the overall limit. So the limit placed on the stress within the part before it would predict failure. And it turns out that we can try to predict when that'll happen by doing some testing. So for example, a fatigue tester might look something like this. So within here I have a test sample and a chuck that provides rotation, and the other end provides a bending load on this component. And as we load this in a cyclic fashion, we would expect to eventually cause the part to fail, and we can record how much stress we applied and how many cycles it took for it to fail. And that allows us to make predictions about how long we expect a part to last. And likely what we will find is that that failure limit is lower than the static failure limit. And so if we were to plot that, we would find that if we plotted the stress at failure, I would get some sort of decreasing plot that shows that the stress goes down until it hits some limit, which we call the endurance limit and label Sn prime in this case. Now, tests performed on a fatigue tester like this are operating under relatively ideal conditions. We try to have high quality test specimens. We try to very tightly control the conditions under which we're doing that. And of course, that isn't reality, right? There isn't some idealized scenario when we apply a load to a car driving down the road. There's all sorts of different confounding factors. So to take that into account, we make predictions about how those confounding factors may reduce the overall stress limit that we have for our part. So we might reduce that limit on the basis of how the loading is applied, the size of the component, the surface finish, the temperature that it's going to be operating in, and perhaps just reliability. Because as it turns out, the prediction for when this will fail is just that. It's a prediction, and it's based on empirical data collected over time, and then the application of statistics, which turns out to be one of the more important subjects when it comes to understanding engineering principles. So we take all these various things into account, and we calculate a new limit for what sort of life we could expect out of a part. And that limit is based on this endurance limit, and then we multiply it by a bunch of these factors for load, surface, size, temperature, and reliability, just as some examples, and take into account all of these various factors that might influence how we expect this part to fail. Now, what do we actually do with that information then? So if we take this, how do we compare the stress some combination of stress that we get from up here and compare it against this new limit? Well, there are a number of theories available to us for how to do that. And one that's somewhat useful to look at or think about, or one tool that's available to us, is called a fatigue diagram. Now, on a fatigue diagram, we take some of these various parameters that we've calculated and we apply them to axes representing the mean and the alternating stress, where we recognize that some of these stresses that we've calculated up here will be constant, meaning that they're not changing with time, and therefore they factor into our mean stress. Also, some of those stresses will be varying, commonly the bending stress, sometimes the axial stress, in that for every cycle of rotation that we see, for example, in our from our wheel, the stress also varies. So that would factor into an alternating stress. So then on our fatigue diagram, we collect those terms and we say that there's some mean stress or constant stresses and there's some alternating stresses. And then we'll take some of our material parameters. So common points to plot on this chart would include the yield strength of our material, which I'll put on both axes, the ultimate strength of our material, and the endurance limit that we've calculated here. So now, if we take those stresses from before and we combine them in some way, we can measure against these criteria and say that I have some mean stresses and I have some alternating stresses, and those produce a plot point. So now, if I go ahead and draw a line from my origin and out, this line represents the various possibilities with changing load. So if I increase the load on my component, I would expect this dot to move out along the line. If I decrease the load on my component, I would expect this dot to move in towards the origin. So then what are my limits? Now, that of course depends a little bit on what theory you subscribe to, but some common options would include, or one common option would include the Goodman line as an example. And the Goodman line says that you take the endurance limit on the alternating axis and you connect that line to the ultimate strength. And this gives us a limit that prevents us from increasing our load any further. So if we go past that point, we could expect failure. Now we need to be a little bit careful though, because through the combination of these various types of stress, we might also just fail statically. Maybe perhaps we fail before we ever see any sort of fatigue. And therefore, we need to remember to include the yield line. So this blue line here represents the yield line, and my red line represents the Goodman line. And these provide unique points. Now, for my particular dot that I've shown here, it doesn't, we don't expect yield failure prior to the failure due to a high number of cycles. So this would predict a fatigue failure first rather than a static failure. Now, how do we get this dot? Well, that is dependent on how we combine the various stresses that we calculated up here. So I said that some of them could be mean stresses, some of them could be alternating stresses. And we can put those together and calculate what we would call the equivalent alternating stress, which is a combination of normal stress and shear stress. And we can do a similar thing for the equivalent mean stress, applying this equation as shown. So then, taking a look at this chart, one thing we can make note of is that if my dot is traveling purely along the x-axis, that would correspond to static loading. Or if I find that my dot is purely on the alternating axis, that would mean that my mean stress is 0 and my alternating stress is non-zero, and that would correspond to fully reversed loading. So once I know my mean and alternating stresses, I can find a corresponding point to match that. And as you might imagine, as this line moves out closer and closer to failure, my safety factor approaches 1. So my safety factor is decreasing, decreasing, decreasing until I hit that intersection point and see failure. Now, this Goodman line is not the only way to represent failure, as I've already mentioned. There are a number of other techniques. This is just one kind of useful one. It's nice from the perspective that it's a straight line, so the calculations for finding the intersection point of these two lines is relatively straightforward, and it gives us a useful tool for how to analyze fatigue failure with regardless to whatever load scenario we end up having. All right, so I hope that was a useful overview of fatigue and some of the different considerations that we need to think about. Thank you.